of course, there's a better explanation. So many of you, of course, know Blakesley. She was a postdoc here for, I think, 5 years, doing a NASA Einstein Fellowship, Hubble Fellowship, and also ITC Fellowship, yeah. So before that, of course, she did her undergrad in Kentucky, and then she did her PhD with Alex Lazarian at Madison, Wisconsin. And then she came here, and then she went off. Now she's an assistant professor at Rutgers, and also an associate research scientist at the CCA, Flatiron Institute. So many of the things that she's worked on we'll hear about, but she's earned awards for her PhD, international recognition from the Astronomy Society of the Pacific, I believe, and then also from the AAS, from the Andy Jump Cannon Award, and also the prestigious Packard Fellowships and the Alfred P. Sloan Fellowships. So this is, I think, a very good CV to have, and we're welcome to hear about what you're doing now.
Thank you. Is this on now? Yeah, great. Well, it's just, I mean, it's really like a homecoming for me to be back here at the CFA, to be like in this room where I spent so much time as a postdoc listening to awesome talks. And like, it's just amazing to see so many familiar faces, also new faces. Just like very nice to be back. And also exciting for me personally to talk about the low redshift Lyman Alpha forest and some of the exciting things we've been discovering at that low redshift regime in the intergalactic medium. And in fact, it's really a pleasure for me to talk about this particular topic in this room because I was inspired by another CFA colloquium that I actually saw in 2014 by Juna Kohlmeyer on this very topic in this very room. So it's just kind of like all the story all comes together. And this work has been done in collaboration with a really wonderful and amazing graduate student at Rutgers University, Megan Tillman, a former Harvard SAO REU student, Alex Gurvich, and then many other collaborators and really friends. So it's been a really fun project. And this is a story about maybe a paradigm shift in a way for the Lyman Alpha forest as we move to low redshift. And I want to start this story telling you a little bit about the history of the intergalactic medium, right? And this is the cartoon picture of the evolution of the universe, not just the intergalactic medium, but also structure formation and galaxy evolution from the Big Bang to the present day. And from the point of view of the intergalactic medium, right, there's some classical epochs of the universe where we could tell this story, right? So early on, right, with the recombination epoch, right, this is where the universe has expanded and cools very rapidly, and we have recombination of hydrogen to become fully neutral in the intergalactic medium. And of course, we can see this very clearly in CMB observations, right? And then our story continues onward to what we call the dark ages, where we hopefully will soon be observing this with 21 centimeter mapping experiments, or maybe we already are starting to observe this regime of the universe where the gas is fully neutral, right? And this is where a lot of structure formation is occurring, and galaxies are forming. This first stars are starting to turn on and really pump up these reionization bubbles to where we finally enter this epoch of the intergalactic medium, where we're in this post-reionization period, right? And this is where we can start to observe the intergalactic medium with the so-called Lyman Alpha forest. And I'll remind everyone what we mean by the Lyman Alpha forest, right? But this is around redshift 7, redshift 6, where all these reionization bubbles have expanded fully. The background UV is more or less uniform everywhere in the intergalactic medium, pumped up mostly by galaxies and also starting to be more excited in the UV by quasars, right? And so this is where we can start to observe the intergalactic medium in the optical. And then finally, fast forwarding all the way towards present day, right? We know that the intergalactic gas is still fully ionized. The expansion of the universe has made the gas densities even lower and lower as we move towards the present day. And the intergalactic medium is hot, right? So this is not just hot from the UV, but also from shocks from galaxy formation. This is more challenging to observe, right? We need to observe this hot gas in UV or X-rays. Why is that challenging? Well, we have to go to space, right? So this is the picture, right, we have of the intergalactic medium. And I will argue that while we kind of understand this green regime here, this post-reionization part, the low redshift medium has a lot of interesting questions still open. Right, so I'll back up and talk about like what is the Lyman Alpha forest, how do we use it to diagnose the intergalactic medium. Then chapter 2 of this story, right, I'll tell you some tales of success from this kind of higher regime, higher redshift regime in the Lyman Alpha forest, around redshift of 2-ish up to maybe 6 or 7, right? So we've gotten a lot of insights in that regime in terms of cosmology, cosmological parameters, what's the ultraviolet background doing in the intergalactic medium, and also just the physics of the IGM. And then chapter 3 of my story, I'll talk about the low redshift regime, right? So redshifts around, less than 1 or so. And, the spoiler of the story is in the title already, right? How do black holes change that high redshift paradigm that I'll tell you about? So the first part of the story will be kind of this green regime, around 1 billion years or so into the evolution of the universe, and then the present day around 8 billion years or so. Okay, what is the Lyman Alpha forest? Just as a little reminder for everyone, right? So if you're looking out into intergalactic space, you'll see background bright quasars that are shining light towards us, and that light is moving through an intervening medium of neutral gas, which is the intergalactic medium. And as that light is moving towards us, it's getting redshifted along the line of sight, and that redshifted absorption line produces what we call a forest of absorption line features at different wavelengths that are redwards towards the Lyman Alpha line, right? So there's this redshifted forest of Lyman Alpha lines. And also, as you can imagine, here you have some Lyman beta, Lyman gamma, and so forth. You have this whole forest of the Lyman series of lines of neutral, which are produced by this neutral gas. And we have a census now of hundreds of thousands of quasars from studies from the 90s and onwards to today at various redshifts, right? So you can imagine you have many background quasars. They're all, we can all shine their light through the intergalactic medium, look at their absorption line spectrum, and if we know the redshift of those quasars, then we can also do redshift studies with the intergalactic medium in terms of the properties of the neutral hydrogen gas. So these are 2 example spectral line observations from redshift 3.6 towards a background quasar. This can be done in the ground-based optical telescopes can do this because of the redshifted Lyman Alpha lines. If you want to look at a quasar that's more nearby, so let's say redshift 0.158 here, you have to go to UV. And one of our main instruments to do that sort of science is the Hubble Space Telescope with the COS instrument. So there's a couple obvious features that you can just tell pop out from these different spectra at different redshifts. So for one, the very high redshift Lyman Alpha lines, they're much thicker, right? So the forest is thicker. This is because the optical depths are much higher, and you have a lot more absorption going towards higher redshift. The cosmic density is much higher, for one, whereas the lower redshift case, the optical depths are less, the cosmic baryon density is lower, and so the forest is less thick. What can we glean from these observations, right, from high to low redshift? Well, one, the IGM must be highly ionized, right? So these optical depths, while they're larger at the redshift, let's say 3-4 regime, they're not fully optically thick, right? So we see an increase in optical depth of the neutral gas, but it's still very, very transparent. So the ionization fractions are like 10 to the -4, 10 to the -5. So the IGM is very much highly ionized in the intergalactic medium up to these redshifts. Right? So we can also, if we go up to even higher and higher and higher redshift, right, this picture I showed you at the start, at some point the gas all becomes fully neutral, right? So this is roughly where this epoch of the dark ages and reionization starts, at some point we should be able to see that optical depth of neutral hydrogen saturate, right? So there would be no more trees in the forest at all, and it would just be like a trough. There'd be so much absorption here we wouldn't be able to see anything, right? And so we actually can see that, and this is the famous Gunn-Peterson trough feature. And around redshift of 6, we start to see those kinds of ending of what we can see in the Lyman Alpha forest from that highly optically thick medium. And another interesting signature of that reionization ending, that epoch ending, is where we can see spatial variations in the Gunn-Peterson troughs and the optical thickness of the forest. So this is really one of our main signposts of the end of reionization. You can also do a lot of cool IGM physics, not just understanding like the cosmological picture, but what's the gas doing? What's its temperature? What's its density? And for that, like if you take this redshift of 6 regime and onward to be the end of reionization, they're an assumption about what's happening to the UV photons in the intergalactic medium. You can say that there's roughly a uniform background at that point. And if you do that, then you can say, well, the IGM is probably in photoionization equilibrium. And you can write down a simple equation for photoionization equilibrium that relates the neutral hydrogen and a photoionization rate with the ionized components, the protons and electrons, times some hydrogen recombination coefficient, which depends on the temperature of the gas. And just based on this photoionization equilibrium, you can define an equation for the optical depth that then can tell you, based on a measured optical depth in comparison to this theoretical one, right, what's the temperature of the gas, what's maybe the photoionization rate, which is something that's of definite interest for cosmology and for galaxy formation, and also the baryonic overdensity of the absorbing gas, right? So all of this can be pulled out from information from the absorption lines. I will talk in this talk a lot about how we measure this photoionization rate and how that comes into play in the low redshift regime. But based on this ionization equilibrium assumptions, right, we can start to say something about the density and temperature of the intergalactic medium. In this regime here, right, this temperature regime of around 10,000 Kelvin and densities less than 100 or so, this is where the Lyman Alpha forest is probing, right, this more diffuse H1 gas. And we now know that in the local universe, so redshift of 0.1 or so and onward, we have a lot more hot gas. So that's this warm, hot, ionized medium. And then out to very high densities here, this is more in the halos of galaxies around the circumgalactic medium and into the galaxies. But this regime here in terms of temperature and density is where we are able to probe this with the Lyman Alpha forest. Okay. So let me tell you about how we use the Lyman Alpha forest for studies of cosmology and how this is really a solid theoretical picture. Because this photoionization equilibrium works so well, we can really do a lot of interesting science. And one thing we can do is measure the so-called ionizing background, right, the UVB. And one way we do this is we count up directly star-forming galaxies and quasars. We get their photon budget. And then we can also compare that budget to the absorption lines in the neutral gas from the optical depth measurements from the absorption lines. And then we can compute here the photoionization rate of H1. And that's what these different models, so there's various papers that have computed models based on the neutral hydrogen gas and observations of the emissivity of quasars and star-forming galaxies at different redshifts. The models more or less agree within a factor of a few or so at high redshift, and then they diverge pretty strongly at low redshift. But basically measuring that optical depth or that column density distribution from the absorption lines will give you some kind of consensus on gamma, which is this photoionization rate. There's another interesting success of this high redshift Lyman Alpha forest, and that comes from the comparisons with cosmological simulations. So hydrodynamic simulations that include dark matter, that include baryons, and various different forms of physics, especially for the baryons, that could be very important for the formation of galaxies and for stars. In the Lyman Alpha forest, as I'll show you shortly, you actually don't even need all this complicated physics to explain the high redshift absorption lines, right? So all this messy baryonic physics, like magnetic fields and stellar feedback and radiation and cosmic rays, right? This actually is not needed at the highest redshifts that we observe the Lyman Alpha forest. We really just need to consider collisionless gravitational dynamics, which would be the dark matter. And then we can almost paint the hydrogen, the neutral hydrogen gas, onto that dark matter, assume something about the background UV, and voila, these cosmological simulations actually can predict the properties of the forest. This is amazing, right? So let me show you some example simulations from the Illustris team, where we're evolving here the universe forward in time from redshift of 4 so onward. This is just adiabatic cooling. There's no star formation physics. There's nothing fancy here. It's just dark matter. And you can see the overall structure formation of these two simulations, one with just expansion and the UV background, and then the other with more complicated cooling, star formation physics, and feedback, and also black holes. The overall structure of the gas, and it's a little hard to see with the light here, but it's basically the same at high redshift. Let's look at some kind of classical papers, right? So this is from Hörnquist et al., 1995, and this was really kind of a seminal paper on this Lyman Alpha forest, matching to the observations from the simulations. This is the column density distribution. I'm going to show this plot many, many times throughout the talk. So you have the distribution of neutral absorbers as a function here of column density. So it's really like a histogram of the column densities in the simulations or the observations. The observations, you can get this directly from measuring the equivalent widths of the absorption lines. And then in the simulations, you can also measure it directly, assuming something about the cosmic UV background field. So what's amazing about this paper is they didn't have, again, any of this complicated star formation feedback physics and baryonic physics. It's really just dark matter, and you have the UV background, and you basically paint the H1 on and like put skewers through the simulations and construct your Lyman Alpha forest. And the data in the simulations matched beautifully. And from this beautiful match, you can actually go back to your photoionization equilibrium equation and estimate directly omega baryon. So this was one of these first measurements of omega baryon from the Lyman Alpha forest from simulations, and it matched very well. So this is really a big check mark for lambda CDM cosmology, that this picture of the Lyman Alpha forest with simulations and observations matched very well, even in the mid-90s. And more modern simulations, more updated, bigger boxes, more particles, better numerical schemes. They also just confirm again and again that this high redshift Lyman Alpha forest picture matches very well the lambda CDM paradigm. And here's another column density distribution plot. So the same plot I was just showing from the Hörnquist et al. Paper. The red here is the simulations. This is from the so-called OWL simulations. And the black here are the data, right? So these are different optical surveys of the Lyman Alpha forest column density distribution. And every time I see this, I'm just like, wow, that is not a fit, right? They didn't fit that. It's just that's how the simulation and the data, how well they overlap. So this is an amazing correspondence at redshift 3, right? And again, what goes into these simulations, right? They only need this photoionization assumption, so they need some photoionization rate. They have a density field, basically that follows dark matter. And then the temperature of the gas is set by the equilibrium between photoheating from the UV field and then the cosmic expansion that's setting the cooling rate. So this is a great news for lambda CDM. what else has been done with the high redshift Lyman Alpha forest? So many things for cosmology, right? So it's really pushed into this world now of precision cosmology. We think we understand it so well, and it matches so well our simulations. So just a couple little examples of really cool studies that have been done with the forest, right, is, for example, setting up lambda CDM versus warm dark matter models. These predictions for warm dark matter models make the Lyman Alpha forest a little fuzzier, and that shows up in the power spectrum of the absorption line. So where that thermal cutoff happens at the very high Ks is sensitive to either warm or cold dark matter models. So this couple different studies have been done trying to distinguish cold and warm dark matter and rule out different models. There's also a lot of exciting BAO science that's being done with the Lyman Alpha forest and measuring acoustic peaks in the forest imprinted on the Lyman Alpha forest. So this is also an exciting line of research that's done with the high redshift forest. And also, there's been a lot of studies that measure cosmological parameters, not just omega baryon, but also sigma 8. Again, looking at the power spectrum of those absorption lines, the flux power spectrum, and relating that directly back to the dark matter power spectrum. So you can measure cosmological parameters. So here's a study from Croft et al., 1998, where they vary sigma 8, and they see how that changes the power spectrum. So you can rule out different cosmological parameters. So if you're doing precision cosmology with data, I would say that means you have a pretty solid physical understanding of all the systematic effects on that data, right? And again, I think the correspondence with the forest and just a simple UV background and the dark matter paradigm that we have kind of put that on solid footing. All right, that's the high redshift Lyman Alpha forest, right? So shortly after reionization onward, what about the low redshift Lyman Alpha forest? So this is, Z less than 1, really more like 0.1 to 0.6 or so is where the UV instruments that we have currently are giving us data. And it's challenging because first of all, you have to go to space, right, in order to get above the Earth's atmosphere. So there's been a couple instruments like GALEX and FUSE and now COS that have given us a number of different absorption line studies that finally around 2014 or so was enough statistical samples of low redshift quasars to really start to do these kind of statistical studies of the forest. Why should we care about the low redshift universe? Like, isn't it everything solved? Someone actually told me the other day, all the new physics will be discovered at high redshift. I was at a KITP meeting. We had a debate. Where will we see new physics? And they were saying, oh, it's all going to be the high redshift universe, right, with JWST and everything. And I was like, well, actually, there's mysteries at the low redshift. And why should we even care? Well, actually, this is still where all the baryons are. They're in the intergalactic medium. At low redshift, there's more and more baryons still in the intergalactic medium, about 80%, right? So most baryons haven't collapsed into luminous objects like galaxies or clusters yet. So this is where at least all the baryonic matter and physics should be looked for and done. Why is the low redshift forest difficult, right? So, the sheer fact that we have to go to space and have UV instrumentation has made it to where we couldn't really do these statistical studies like we have done in the higher redshift regime until about 10 years ago or 8 years ago or so. And then, of course, from the point of view of cosmological simulations, right, all of those messy baryonic feedback effects seem to become more and more important as you go to the low redshift regime. So like, for example, non-standard heating sources in the intergalactic medium, like shocks, things that are more complicated than just assuming a background UV field, become more and more relevant. So what do we see in the low redshift Lyman Alpha forest, right? So there was this really nice study by Danforth et al., 2016, which compiled absorption lines both from COS, Hubble COS, and also GALEX and FUSE and others to create a catalog of low redshift absorbers. And shortly after, around that time that it was published, there was a really nice paper from Kohlmeier et al., 2014, and Juna Kohlmeier actually came here and gave a talk exactly on this and got me really interested in it. So the Danforth data here is in magenta, and the Kohlmeier paper looked at gadget simulations. So these are SPH hydrodynamic simulations that at the time had star formation feedback and so forth. The Hart-Maddow 12 UVB, so at the time that was one of the more updated ultraviolet background models, and showed that there was this extreme mismatch between the gadget simulation here in black in terms of its column density distribution and the Danforth et al. Absorption lines. And in order to rectify that difference, you would actually need to take the gadget simulations and increase the UV background by a factor of 5. And if you did that, you would get that blue line, right? So they would match. So you need a factor of 5 more ionizing photons in order to match the cosmological simulations with the observations, which is a little bit shocking, right? So where are you going to get those photons? Where are they going to come from? And just to give a sense of how a factor of 5 over that Hart-Maddow 12 would look, here's how it would look. So you have your gadget simulation with the Hart-Maddow 12 UV background, and that's just generally what the structure looks like. And if you increase that by a factor of 5, it looks like this. Right? So it's almost, if you go back to your photoionization equilibrium equation, right? So if you're changing gamma here by a factor of 5, that's changing the density, which in turn changes the column density distribution and so on. It's like you're burning that Lyman alpha forest down, and you're getting less and less a gas that's able to absorb in neutral hydrogen. So where are you going to get a factor of 5 more photons? Well, right, you could say, well, since Hart-Maddow 12, right, we must have had more advanced or updated UV background models, right? That gamma surely wasn't right. So let's take a look. What's been done since then? Right? Can these updated UVB models save the day? So here I'm showing the factor of gamma relative to Hart-Maddow 12. So here's Hart-Maddow 12, right? So it's 1. There have been many other models that have been proposed since then, and so far you can get about a factor of 2.5 or so more ionizing photons, and that's just from changing maybe the escape fractions of the galaxies, right? So quasars are putting out photons, but of course galaxies are as well, and the models are very sensitive to the escape fraction, like how many UV photons can actually get out of the star-forming galaxies. That's definitely an uncertain parameter, but a lot of observations suggest that that's for many galaxies is less than 1%, and so you really have to dial up the escape fractions a lot if you wanted to get up to 5 times more ionizing photons. It seems unlikely that you have escape fractions of like 10% or something like that. So it seems that the problem can't be resolved just from the UVB. But what we did here at CFA with a very smart REU student, Alex Gurvich, was just say, well, all right, let's see if it was something maybe with the gadget simulations, that other simulations maybe would show something different. And it turns out when we looked at Illustris, we didn't see this problem. In fact, it didn't match perfectly, far from it, but it was definitely different from the gadget simulation. So the black line here is the Kohlmeier 14 study, and the green line here is the original fiducial Illustris cosmological simulation. The magenta lines here are the Danforth 16 data. So you can see that the Illustris simulation has significantly less neutral hydrogen absorption. It's either hotter or there's more ionizing photons. Something's going on there, right? So what we ended up looking at is, what is causing this difference between these two different simulations, right? The UV background is something that's known that's different between those two simulations, and we can account for that. But what is affecting the rest of the differences? Is it resolution, stellar physics, AGN physics, et cetera, et cetera? Right, so the UV background was kind of an obvious thing to check first, and we know that Illustris has a different UV background than the gadget simulations that use the Hart-Maddow UV background. And so the UVB alone couldn't explain it, right? And the simple test we did there was we just said, okay, let's run Illustris now with the Hart-Maddow 12 background. And of course that, it's less ionizing, so there's more in absorption that we'll see there, but it's not enough to explain fully the difference with the gadget simulations. Right? So some additional heating is maybe needed. Maybe stellar feedback is doing something. Well, it's not. So the different stellar feedback models that we checked with the numerical simulations, they're basically lying right on top of each other here. So if we have no stellar feedback or a lot of stellar feedback or the fiducial model, it just wasn't able to explain it. And it makes sense, right? Stellar feedback is going to affect really close into the halos and the galaxies, and maybe the CGM, of course, around the galaxy. But into the intergalactic medium, you have to have some kind of feedback mechanism that will affect megaparsecs away from the halos. And so stellar feedback seems to not be able to do that. Well, the talk title probably gives away the story, right? So AGN feedback seems to be able to do the trick. And visually, you can see that here. So this is a cosmological simulation with AGN feedback, so actually the fiducial illustrious numerical simulation. And then when we turn off that AGN feedback, right, the galaxies, of course, look very different, and people have known that for a long time in order to explain galaxy colors, gas fractions, star formation. You need that AGN feedback. It also affects very strongly the Lyman Alpha forest and the IGM in general, right? And so without AGN feedback, you can see there's a lot more neutral gas. The color here is actually the column density of neutral hydrogen, which would show up in the Lyman Alpha forest absorption lines. You see it looks dramatically different with and without AGN feedback. And again, one thing that could be going on here is the heating. So your photoionization equilibrium equation, you also have this dependency on temperature. So in addition to changes in the UV background, right, once you go to lower and lower redshift, this AGN feedback becomes more and more important. It acts as a source of heat, and it also can redistribute the gas around the intergalactic medium. And so that's where the third chapter of the story comes in, how black holes change that high redshift paradigm when you go towards lower and lower redshifts, how black holes actually add a lot of heat to the intergalactic medium to the point where you can no longer estimate that UV background gamma based on just the forest statistics as people had previously done. Well, it's really amazing to think about black holes affecting the intergalactic medium, right? So this is a cool movie from ESO showing a zoom in to our Milky Way center, zooming into the supermassive black hole. And I love this movie because it gives you a sense of the size scale, right? Like the galaxy zooming in 8.5 kiloparsecs all the way into the galactic center, right? In the intergalactic medium, we're talking about megaparsec scales, right? So the discrepancy between the size of the black hole and the energetic feedback that's able to heat the medium is just simply enormous. And I think it's incredible to think about how these black holes are able to launch jets and heat and ionizing this intergalactic medium, right? So it's a huge discrepancy in scales, right? And so I want to show you a couple examples of how this AGN feedback can actually affect the IGM, and also in terms of looking at different AGN feedback models, right? Because what's under the hood of these cosmological simulations is a subgrid model, right? And it's a model that's been calibrated to match properties of galaxies, but not properties of the intergalactic medium, right? So, a simulation like Illustrious, which I was, showing some results from before, or the updated now Illustrious next generation model, one of the main updates between these models was changing the black hole feedback prescription, right? How you seed the black hole, how the black hole grows, is an important difference between all these different cosmological simulations, and also how these black holes eject their feedback, right? So Illustrious, one of the big changes here was this difference in how it blew out these thermal bubbles in the low accretion mode. So one mode here has this hot thermal bubbles that inflate and expand out into the intergalactic medium and kind of naturally act as a heat source there. And this is really the reason why the gadget simulations and the Illustrious simulations from our earlier study looked very different. It's because of these hot bubbles from the black holes expanding out. In TNG, they changed this bubble mode dramatically to a kinetic feedback mode. for low accretion rates. And so now there's kicks to the gas that are moving out isotropically into the intergalactic medium, and it doesn't blow out as much gas, and it also heats the gas less violently. So let's look at the difference in the intergalactic medium, right? So first of all, the particulars of the model have a huge effect, right? So this is the column density distribution, again, showing this. The Danforth data is in blue, so this is the observational data from COS. Illustrious in red, and then the black here is TNG. So right away, you can see that the changes in the AGN feedback model dramatically alter the distribution of column density in the low redshift intergalactic medium. These models have the same UV background, right? So they both use the Fauché-Guillier 2009 background. So this is not due to the UV background. This is entirely due to the feedback. And this, if you showed a cosmologist this in the 90s when they're doing all this precision cosmology with the forest, they'd probably be kind of freaked out, right? Because everything about this amplitude of the column density distribution should be set by the UV background or maybe your dark matter model, right? So the fact that feedback is affecting this so strongly is really important at the low redshift regime. You can also visualize the changes here. So here I'm showing Illustrious, the column density and temperature map of Illustrious, and TNG here at redshift 0.1, which corresponds to these lines here. And you can just see dramatically the TNG column density distribution in Illustrious. They look entirely different. And of course, also the temperature maps, right? This hot gas is being blown out by those radio bubbles in Illustrious, and in TNG, it's much more gentle in terms of its heating and redistributing matter than Illustrious. What does that look like at high redshift, right? Because at high redshift, things should behave nicely. And indeed, they look very similar. So this is the same kind of picture here, but at redshift of 2. Right, so these are the column densities between Illustrious and TNG. They look like very similar in terms of their distribution, and the same with the temperature maps. So it seems that this shift from the Lyman Alpha forest at redshift of 2 and onward, tracing just the UVB and the dark matter, is still solid in these simulations, which is a good thing. But as you transition down to low redshift, something dramatic is happening with the feedback. Neither of these feedback models include bipolar jets, right? So we know AGN feedback, right, can affect up to megaparsec scales because we observe this directly in radio observations with, for example, synchrotron. We see that megaparsecs out from the centers of clusters and massive galaxies, we see these beautiful radio lobes that can move out into the intergalactic space. And so we know that there's heating and there's matter being redistributed from bipolar jets. There is a simulation that includes bipolar jets, and that's the SIMBA cosmological simulations, and I'll show you some results from this particular simulation. It has a different AGN feedback model than Illustrious and Illustrious TNG, and these bipolar jets, you can see they start to turn on once the halos get massive enough to host supermassive black holes. And by redshift less than 1, those bipolar jets have filled the intergalactic medium with very hot gas. And so just visually, you can imagine what the column density distribution might look like, right? It's a lot less neutral gas, right? The medium is just simply too hot to host a lot of neutral gas. And again, showing you the column density distribution from the Danforth study in blue, and now the black line here is the fiducial SIMBA cosmological simulations. It looks much better, right, than the original Illustrious or even the gadget simulations from Kohlmeier. In fact, it fits very well from column densities around 10 to the 13.5 onward here, and it's even pretty good at the very low column density regime as well. So this model is significantly heating the IgM, reducing the neutral fraction greatly. So turning off that jet mode, right, we can directly see the effect of the jets, right? So the red line here is SIMBA, and it still has the radiative AGN feedback mode, but it turns off those jets. And then what happens is you get this red line here. So the jet mode in particular has the most impact on the intergalactic medium in terms of its heating. you might be thinking, well, what about, the degeneracy with the ultraviolet background model? Like, what if we were to mess around with the galaxy fractions, or somehow we just don't have a good handle on that? Well, we can actually see which is the best fit model if we just let the UV background run wild, right? So we can tune the escape fractions however we want. We can get whatever UV background we want. And we can see which model is the best fit. And it turns out the case with AGN jets is still the best fit model. If you were to look without jets, you'd have to pretty dramatically change the UV background to get a fit. I think more dramatically, at least, than any of the current models are predicting. So it seems that the best fit model would be a bipolar jet model, probably also a more ionizing background than the Hart-Maddow 12. Tuning those two things together, I think, would be really important for future work. Just some more fun visualizations to visualize the AGN jet feedback, right? So this top row here is with jet feedback. And you can see here the column density projection, the temperature projections at redshift of 0.1. And if we turn off the jet feedback, the column density, there's a lot more higher column density material, not so much in the low column density. You don't get these big holes in the intergalactic medium. And also the temperature distribution is dramatic. So these jets, again, are pumping up a lot of heat in the intergalactic medium. This would change, of course, that temperature density diagram that I showed at the beginning of the talk, right? So here we have this Lyman Alpha regime. And then with AGN jets, without AGN jets. So this creation of the WIM is also a very dramatic example of what the jets are really doing here. They're actually pushing gas, heating gas, but also redistributing the gas. That's what these red lines here are showing. Redistributing the gas into this hot diffuse phase versus this warmer or cooler diffuse phase that is traced by Lyman Alpha. And this effect, this movement of gas, these red points from this diffuse component up into the WIM is really starting around redshift of 2 in SIMBA, or redshift 5 to 2, it starts to transition, and then it's a dramatically volume filling by redshift 0.1. Okay. Let me show now, since I'm getting close to time, a couple studies we've been doing on the redshift evolution of this effect. Also looking in comparison of these different cosmological simulations with the CAMELS collaboration, which is running many thousands of realizations of simulations with these different models, the illustrious TNG model, SIMBA model, Astrid model, and other cosmological models as well that change the AGN feedback, that change the stellar feedback, and also look at the different hydrodynamics. So, I'll run this little movie again to show just the dramatic difference, right, visually in the intergalactic medium between these cosmological simulations, right? SIMBA with the bipolar jet model dramatically heating the IGM, illustrious with this kinetic mode, and Astrid with kind of a similar, also kinetic mode for their feedback, being much more gentle on the intergalactic medium. There's not as much heating, and there's also not as much gas being thrown out. What's the redshift evolution look like, for example, between SIMBA and illustrious TNG? And these now have the same UV background. So we've rescaled illustrious TNG to match the SIMBA UV background. So these are the same. So this effect you're seeing as a function of redshift is really due to the black holes entirely. And so around redshift of 2 or so, things look good. They look like reasonably similar, which is what we expect from this kind of earlier cosmological paradigm. But as the black holes really turn on and grow and become more massive as they go down to lower redshift, the column density distributions diverge dramatically, even for the same UV background, right? So this is really, I think, troubling for studies that use the Lyman alpha forest at low redshift to estimate the UV background, right? Because the AGN physics, which is highly unknown, might be making trouble for us. Right, if we just look now, this is a still shot of TNG versus SIMBA. Right, so the SIMBA lines here are in black, and we also have the no jet mode in the dashed black here. And then the red lines here are illustrious. And if we turn off illustrious kinetic mode, nothing really happens. So the jet mode seems to be the most important AGN feedback mode for affecting the Lyman alpha forest and getting out of the halos into the intergalactic medium. What about changing the AGN parameters, right? So what if we change the jet speed, or we change the jet momentum, right? So these AGN models, they're calibrated on the galaxies, but maybe there's not one best model, or maybe we need to rethink our models. How does this affect the Lyman alpha forest in addition to the galaxies? And for this study, this is work in progress, we're using the CAMELS cosmological simulation suite. So this is many realizations of simulations like illustrious TNG and SIMBA and ENSO and ASTRID, all of these different cosmological simulations. A team of people have gotten together and said, let's create thousands of universes with different cosmological parameters and different feedback parameters. And then we can do cool things like machine learning, for example, because we have a huge training set. But we can also study how those different subgrid prescription models are changing the universe. And in particular, I'm interested in how these different models are changing the intergalactic medium and the Lyman alpha forest. And so just as a little teaser of this, right, we can change the SIMBA AGN feedback, jet speed and momentum flux. So these are things that the CAMELS team has tuned and played around with. So they're calling them AGN2 and AGN1. That's just code for jet speed and momentum flux here. And you can see that the jet speed in particular can really profoundly affect the column density distribution, right? So if you turn up the jet speed, you get these redder lines here. So there's less neutral gas. It's kind of blowing the neutral gas up and heating the neutral gas dramatically. The momentum flux maybe not affecting it so much. And actually, the jet speed alone is kind of creating a change that you would be able to see if you turned up the galaxy escape fractions and had a higher UVB. So there's some maybe degeneracy with the UVB and the overall jet speed. And obviously, the largest changes here in the column density distribution are happening at these lowest column densities. And there's less of a distinction here as you go to higher column densities. There's another interesting effect we found, and that's with the stellar feedback, right? And so originally I showed you from our earlier study with illustrious, stellar feedback didn't do anything to the intergalactic medium, right? Okay, the stellar feedback is confined to the CGM, the halos. It's not really getting out megaparsecs in scale. And so we were surprised to see when we changed the stellar feedback subgrid parameters, like for example, the stellar wind speeds or the mass loading from the stellar feedback, there were dramatic changes, especially with the wind speed in SIMBA. And at first we wondered why. How could that be? Because we had found something different earlier. And after some investigation, what Megan Tillman had found is that she sees that the stronger wind speed is significantly suppressing the growth of black holes in the simulation. And so there's a feedback loop here, a really interesting one where changing the stellar feedback physics is changing things in the galaxies, which may be no surprise. It's suppressing the black hole growth, and that in turn is changing the Lyman alpha forest. So all of these things are interconnected and related. And here's a fun movie that Megan's made with the wind speed parameter. So this is low wind speed, the fiducial SIMBA run with their fiducial wind speed model, and then very high wind speed, right? And so you can see when you have very strong stellar feedback winds in the simulation, it dramatically changes the temperature of the IGM and the column density distributions, which is a direct effect of the black hole growth. So all of these feedback processes in these simulations are connected and dramatically affect not only the galaxy properties like the colors, the gas fractions, the star formation, but also the intergalactic medium. And I want to end on talking about at least one implication for this study. I think there's many implications, but for upcoming observatories that are interested in looking at neutral hydrogen, in the intergalactic medium at kind of low to moderate redshifts, these effects might become important. And an example of an observatory that's targeting 21 centimeter observations at redshift like 0.8 to 2-ish is this HIRAX project. So this is a hydrogen intensity mapping experiment that will be probing dark energy and the BAO effect. And all of the models so far, of course, are this standard cosmological paradigm for the forest and for neutral hydrogen, which is to look at just the UV background effects and just the dark matter model effects, and doesn't really take into account these AGN feedback effects as of yet. This is something I think we'll be working on in the next couple of years, is seeing how the AGN models will affect the 21 centimeter mapping experiments, which are going to be targeting denser molecular, or denser neutral hydrogen gas in the intergalactic medium. So to conclude, the takeaways here, the one thing I'd like you to take away is the high-redshift Lyman Alpha forest. The story there is very, I think, complete in a way. It's a happy place for cosmologists, right, where you can do precision cosmology because the intergalactic medium is very well behaved in terms of the physics that it follows. But the low redshift forest is messy, right, and that's because all of this baryonic feedback effects start to take over and create this big forest fire in the Lyman Alpha forest, right? And this change in the neutral gas is very sensitive to the particulars of your feedback model. It can have a dramatic effect, right? TNG versus illustrious versus Simba, like however you do your subgrid model for AGN feedback, it really matters. And the UVB measurements, therefore, at low redshift are kind of in danger because we don't really know which model is right. We don't know which model is the correct model, right? How much heating should we really expect from AGN? We don't actually know. All we can say is, which models are best fitting the data. And that data includes the galaxy properties as well as the forest. But I think, again, the good news here is we'll be able to now use the Lyman Alpha forest as a way to calibrate these AGN feedback models. And this is something we're doing right now. We're kind of working to see, if we updated the UVB and the AGN models together, like which model would be the best fit. So stay tuned. Thank you.
All right, let's quickly take some questions. Yeah. We can repeat the question.
Great talk. I thought that was super clear and really nicely structured. So you identified like at least two knobs of these, the AGN wind speed and the stellar wind, that make these distributions go up and down a lot. So how optimistic are you that, like, are we ever going to constrain those well enough to measure these things, or what?
I think we will. I mean, those knobs are pretty dramatic in the camel simulations. So I think if you took, like the very dramatic stellar wind speed or the very dramatic jet speed case, and you then looked at the galaxies that simulation produces, they will have, incorrect looking gas fractions or not enough star formation. The galaxy colors will not match observations. So I think with constructing these models, it's a fun theoretical exercise to just see how changing these things affects the observables, but at the end of the day, you would want your model to try to reproduce as many observables as possible.
Angela?
Has someone looked into the different distributions of metals in the IGM of these different models? They must be very different, I'm guessing.
Yeah, so with the metal lines, mostly they're tracing around the CGM, like around the halos. It's difficult to see, metal lines that are really out in the intergalactic medium proper. So people are looking not only at Lyman Alpha, but also Lyman Beta and helium-2. But the metal lines tend to be more concentrated in the halos.
I see, okay.
Yeah.
Floor?
Oh, I was just curious, you were mentioning like camels. So I was wondering like how the people like come together to create that, and like are there any like challenging like database storage challenges that like how you can overcome those?
Yeah, no, it's a big collaboration. It's grown massively actually over the years. So now, in addition to like illustrious TNG, Simba, there's this Astrid simulation, there's also Enzo, Magneticum. There's like 5 or 6 simulations now that are represented, and they all change. There's tens of thousands of simulations actually, and so it's a data storage challenge. And at the Center for Computational Astrophysics, there's actually a whole scientific computing team that is there to assist scientists with projects like that, and so they actually have dedicated storage at the Flatiron Institute, CCA, for that challenge.
Yeah, Charles.
So thanks, Blake. This is great. You almost answered the question I was going through the talk. The Hyrax, is that the ion centimeter?
Yep.
Will that be able to detect neutral hydrogen that's directly associated with known absorption line features?
The challenge, I think, with that is the beam of Hyrax is very large. So it will definitely have overlap with individual absorption features, but the beam will probably encompass several of those features.
So there's enough spectral resolution maybe that they'll separate them out, I don't know.
Yeah. Yeah, if there's like a clustering of absorption lines, in one place versus another, then maybe Hyrax would be able to separate those out. That's an interesting question.
Oh, one up here, yes.
Yeah. Hi. Question for you. You parameterize specifically the AGN jets and the stellar winds, but what about the AGN winds? How does that fold into these simulations, and what kind of an impact do they have relative to the other two?
Yeah, well, we looked at the momentum flux, but the Simba model that I showed here, so TNG also has changes in the way that they parameterize the kinetic mode, which is more of a wind in the sense that it's isotropic rather than a jet, which is bipolar. It doesn't seem to change things at all. So if you were to look at this isotropic TNG wind-like mode, it has no dramatic effect on the forest, as opposed to the bipolar jets, which really, they decouple from the interstellar medium and they really move very far out into the intergalactic medium. There we see a big effect when we change that parameter.
It might be an interesting thing to keep exploring, because there is increasing evidence that these AGN winds can be very powerful in the case of ultrafast outflows, and in fact not isotropic.
Oh,
not
okay.
quite as bipolar as the jets, but definitely conical in nature.
Yeah. I think the collimated aspect of the jets, or wind, like the collimation actually really allows it to move out into the intergalactic medium, versus the other, more isotropic feedback modes, which stay closer into the halos.
Thanks.
Yeah, with that, let's thank the speaker again.